Hello again. Today we're going to be looking at the Signal Hound BB60C. This is a real-time spectrum analyzer. It's got a 27 megahertz bandwidth. My wife bought this analyzer for me back in August as a birthday present. I had two old SWEP type analyzers that I'm using this to replace. One was a Tektronix, the other one was made by HP. This outperforms both of those spectrum analyzers with ease. The only thing I can't do with this is this has an upper bandwidth of 6 gigahertz, and my old HP was good to about 24 gig. And it was rare I ever used the analyzer much above 6 gigahertz anyway. This thing actually will fit basically in the palm of your hand. You can see it's quite small, very light. The analyzer that this replaced was a big 19-inch rack mount, probably weighed 50-60 pounds. It's got a nice extruded aluminum case. We can see it has two BNC connectors on the back. One of them is our 10 megahertz reference, and the other one is a trigger. A couple of things I don't like about it. One of them is it uses an SMA connector. I have my own torque wrenches to set that, but to me, again, this is just kind of a poor choice. Another thing I don't like about it, it's USB 3 based. When I first received it, I tried it with my old laptop. That was running Windows 7, and it's an i7 processor. Obviously, it supported USB 3. This wouldn't work with that basically at all. Any of the real-time operations would cause the software to crash. I ended up speaking with Signal Hound about that, and basically I ended up buying a brand new computer to run this with. And still, the communications to this are not proving to be very reliable. Typically what I'll see is the green light will go active, and basically their software called Spike stops communicating with us. I can go under Device Manager, query the Signal Hound. It says there's no problems with it. If I disconnect the driver from within inside control panel and then restart it, Spike will start working again. If I exit Spike and reload it, it can't find this device, even though the Device Manager finds it. If I unplug this and then plug it back in, of course, Spike will go ahead and find it again. So it looks like whatever happens, this thing hangs in some state where it just basically can't communicate with Spike. Again, the LED is green when this happens. I've probably seen that happen maybe 10 times the whole time I've owned this, and I've put quite a few hours on this thing by now. So again, it's rare, but it does happen. I guess you should be aware of it. They recommend that you don't use this thing with any kind of an extension cable or off of a hub. I ended up buying a hub for it along with some good extension cables, and I really haven't any problems with any of that. The communications problems I'm talking about happened even with this thing plugged directly into the PC. Another thing I don't like about it is it does run a little warm. You can see there's no on-off switch on this whatsoever, and there's no way to disable it completely through the USB port or put it into a low power mode. So what I've got here is a small fan I've just adapted to a USB port. I plug this in, and I use this basically just to blow cold air across it. And when I'm done using this, I have to turn the hub off, or I unplug the hub from the power. So it is a powered hub, and that's how I turn it on and off. To me, it would have been nice to have this thing go into some kind of a sleep mode if you weren't using it, or again, just having some way to turn it on and off without having to unplug it. So the specs and the manuals for this are pretty good. I would recommend, if you're interested in buying one, that you download all the information and just have a look at it yourself. So a while back I bought this Extech meter. This is an EX540. Again, I bought this brand new. The meter's had a lot of problems though. It is functional now, but you notice it comes with this RF link. So for this video, I'm going to look to see if we can decode the data between these two devices using the Signal Hound. And hopefully from running this test, we can get a fairly good idea what the limitations of this Signal Hound are. So when I first received this meter, again, I tore this thing apart, had quite a few issues with it. I never actually tested the RF link. So I went to plug this thing in, and sure enough, it would not communicate with the meter. And the first thing I noticed when I flipped it over is it only had this one screw. These two screws here were missing. You know, these are self-tapping screws, and there were threads cut into the bosses in the plastic. So at one time these screws had been installed and somebody had removed them. So I assumed that with it not working, somebody had taken it apart, tried to repair it, and then only put the one screw back in, and of course they didn't fix the problem. So when I took this thing apart, what I noticed was a lot of the wiring had frayed. So none of it was broken and none was shorted, but you could tell who had ever had this thing apart was definitely twisting this thing up quite a bit. So after I cleaned up the soldering and re-glued the harness, I started looking for the real problem, and it turns out that one of the solder joints for one of the ICs on here had never wicked to the pad. So I went ahead and I checked all the rest of the soldering, and I fixed that one bad joint, and this thing sure enough fired right up and worked just fine. Okay, I'm going to demonstrate the software that's supplied with the meter. Currently you see I have the USB adapter installed in the PC, and we'll go ahead and turn on the meter. This is currently attached to my function generator. I've got a sine wave output and it's sweeping between plus or minus 500 millivolts. You enable the RF link on this by hitting the backlight key and holding this for like a second. And we can see now the LED on the receiver is starting to blink. And you can see in the upper left corner that the antenna icon is now flashing. This is looking at the Extech software. We just select the communication port here in the upper left. In this case we'll use COM 4. We connect to the meter and you can see it immediately starts updating the display. We have a table here that shows the function that the meter's in, the output voltage, the unit, and the timestamp. You can select this zoom function. So we'll open up another dialog box. And you can see now we have cursors that we can take some basic measurements with. And we can also do recording with this. The program itself is fairly simple. There's not a lot of features to it. This is a program that I found online that somebody had wrote. The Extech dongle mimics a standard communications port. So this program opens up a communications port, sets it to 2400 baud, 8 data bits, 1 stop bit. This is the raw packet from the dongle, and we can see the very first nibble starts off with a 1, and then a 2, 3, 4, on up to E. So I'm hoping that we can use this information to help decode the actual RF data. Alright, so you can see I've got a small antenna. This is attached to our signal Hound. I'm just going to lay this on the table. And again, I have the small transceiver attached to the PC right now, and that's on the other side of the room. We'll turn on our meter. So let's go ahead and have a look at spike. This is the main menu of spike. You can see we're sweeping roughly from 9 kilohertz up to 6 gigahertz right now. What I can do is enable another trace, and we'll set that to our max hold. We can get a better idea where these peaks actually reside. So there's one at about 4.5 gig, 3.6, 2.7, this one's 2.4. So here's our Wi-Fi connection. 1.9, I'm not quite sure what that one is, and 915. Well, that 915 megahertz is an oddball because that's right in the IMS band, and I suspect that that is our transceiver. We could just center around that peak, and let's go ahead and we'll zoom into this a little bit. And it looks like there's a couple of different peaks. We'd kind of expect that. There's 2 different transceivers, so the antenna is located at 2 different distances from each. They also probably have different power levels. You can also switch this to real-time mode. And now we get a real good idea what these 2 different transceivers look like. You can see the one radio here in the bright red, and the fainter yellow are off the other radio. If we switch the menu to 0 span, we can get a better idea what's going on. So currently I've got my sweep time set for 380 milliseconds. So this will probably be the meter, because that's going to be sending a lot more data down to the PC than what the PC is going to be sending up to the meter here. So we can actually send this data to the PC. We give it the amount of time that we want to save the data for. Let's just try it at 2000 milliseconds. Right, so 2 seconds here, it's going to save. We give it our sample rate. This is 625 kilosamples per second. And we just hit start. And that now is collecting all that data. Of course, it doesn't update the screen until it's done. And that stores it off into a file. And then we can go ahead and post-process that using software like LabVIEW or something. And here again we can see the 2 different frequencies, so definitely this is just a 2FSK modulation. I wrote this software. This is a post-processor for the IQ data, and I'll just go ahead and load up the file that we just created. And again we can see the 2 different frequencies up here. Let's just go ahead and we'll zoom into this a little bit. And here's our raw FSK data. So literally I could take this IQ data with LabVIEW and I could actually decode this back to the binary data. So another way we can view this data is using Spike. So Spike actually has a demodulation built into it. So we hit Modulation Analysis. And we can see we've selected 2FSK up here. Again, we're at 915 megahertz. And we have our input power set to minus 10 dB. And you can see our eye diagram here. It's definitely locked in. The problem that we have is this. So the baud rate on this signal is quite slow. And we can see that. Again, we'll kind of zoom in here. Currently this is 20 milliseconds across from here to here. We can actually calculate the baud rate off of this. And so I know that this is transmitting at 2400 baud. And you can see what I've done is I've set the sample rate up here to 9.6 kilosamples per second instead of 2.4. And the reason I have to oversample this is if I run this at 2400, this will not allow me to select the IF bandwidth wide enough to get the 2 peaks in. And you can see here the problem is because we're running 4 times oversampling, when I look at my binary data, I have quite a few zeros in a row and then quite a few ones. So the data doesn't look right, and there's no way inside of this software to decimate that data to compensate for our 4 times oversampling. So this is another thing I don't like with this software. I'll tell you another thing I don't like with this is they have this idea of a video trigger. So normally what happens is the radio is off and the thing would just sit there and try to run a pattern check on noise. And it's not going to find probably the signal I want, but it doesn't matter. What ends up happening is it times out after so many symbols are reached, and then it just shows you whatever it had. Really what we would like to do is have the radio turn on, hit this threshold limit, and then start hunting for the pattern that I want to look for, and then have a way to decimate the data, or allow me to change this IF bandwidth independent of what I'm setting my sample rate to. So what I have to do with this is collect all my data and then transfer this thing again as a text file, and the only way I can do that is through the clipboard. So again, we'll set this to video trigger. I'll set this to, you know, some massive number of symbols. And we'll hit the single sweep. And you can see that's too much because we're down in the noise where it lost lock. And up here I can display this data as hex. The software doesn't allow me to skew this by any number of bits, which is kind of unfortunate because you can see it's displaying a E01FE, and you can better bet that this is going to be a 00FF. But I can't get rid of these initial 3 bits. So let's just take it down. We'll try like 1200 symbols. Now what I can do is copy this data into the clipboard. And I can bring up a text editor. We'll just use Notepad. And I hit edit and paste. And here's our binary data. And then I'll just go ahead and save this off to a file. And we'll just call this binary 8. So this is just another real simple LabVIEW program. We can run this and we'll select our new file. This is my original raw data. So here's my 1200 symbols. And this is my decimal data. As you can see, 31, 31, 31. If you may remember, I was sampling at 4x over what the actual data rate was. So what I'm doing is I'm going to look for 4 consecutive bits to be all the same value. And once I have that, I'm going to consider that a trigger, and then I'll realign my data. And that's what you see happening here as I've thrown out these initial 3 bits and I've realigned my array. Next, what I'm going to do is decimate that data. So each one of these 4 bits will be combined into 1 bit. So the first 4 bits are low, so I get a 0. Next 4 bits low, I get a 0. Then 4 bits are high, I get a 1. And then the next 4 high, I get the next 1, and so on. So the last column here is I'm displaying this data in hex, and we can see I get my 33, 33, 33 on down, and then 52, D2, or D4, AA, AA. But basically none of this makes a lot of sense. We're also only looking for like 10 bytes of data. So the next step is we have to actually figure out how this data is encoded. So to figure that out, what we're going to do is use an oscilloscope to actually look at that serial data and see how they're programming the chip. You can see I've attached a small 8-pin connector to our RF board, and I've got a ribbon cable plugged into it, and that's currently attached to our oscilloscope. I mentioned too, these are my Handtech oscilloscope probes. See, this is the manual form. These are the PP150s. I don't remember what these cost, but I think it was like 2 of these for 20 bucks or something, or it was just under $10 each. I did a review for these probes. They actually work quite well. These are the accessories. You can see they come with a little color coding. So I've got the yellow, red, blue, green, and those coincide with the color of my traces here. These are selectable between a 1 and a 10x. I think I've had these for a little over a year now. I haven't had any problems with them. I like using these because I typically don't need anything all that good around the lab here. You know, if we're just trying to decode some serial data, these are fine for that. And for my own testing, at least the probes that I received, the bandwidth for these is every bit as good as the LaCroix probes that I own. LaCroix offered me the serial communications package for the 64XI, and we'll go ahead and use that to decode the messages from this board. So if we just set this to normal trigger, the yellow is the data going to the CC1101, the red's the clock, blue is the chip select, and the green is the data coming back. And we can see that it's continually sending a 34. So what we're going to do is set the oscilloscope to single shot. We're going to go ahead and plug in the USB adapter, and then hopefully what we'll do is collect how they initialize the CC1101. And that should give us some insight as to how to actually decode the RF signals for this. So again, we'll just set it to single shot, and I'll plug it in. Now what we can do is write this off to this flash drive over here. So we just hit export table. If you do configure, you can see I've got time, data, and then my bit rate, which is all I really need is just the data. I just hit export table. You can see I can zoom into this if I want. So we can see the first byte is a 36 followed by a 30. So the next step will be to take this data and decode this by hand. Here we're looking at the data that we just pulled off of the LaCroix. And again, this is the data being sent to the CC1101 during the power up. What's interesting is when we look at the data that's coming back from the CC1101, so we get this 0F, 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 11OF, and then this becomes very interesting. So we get 10, 20, 30, 40, 5. This section of data is actually what's being sent down to the PC. So the next thing to do is decode some of this data, see how the radio is being set up. Then we'll see if we can figure out how to relate the RF signals into the actual binary data. So I've started to decode some of this. First thing it does is it turns off the synthesizer and it resets the chip. But then it starts programming up all the registers. So if we look at the frequency synthesizer, for example, this is at address D, E, and F. They're writing out a 2331 3B, which is 2,306,363. So the equation, according to the data sheet, is 26 megahertz. That's the crystal frequency that's actually used on the board, divided by 2 to the 16th times this value, and that's 914,999,969. So that is the base frequency of the radio. Another one is this modem configuration registers. When we look at these, we can calculate out what the baud rate should be. And again, the data sheets give you an equation for this, and if I look at the registers and what they're being programmed, it's actually 2,398.97 baud, but we'll round that up to 2,400 baud. And you can see that they're using 4 preamble bytes. But if we look at the modem configuration register 2, this is really the answer that we're looking for. So they enabled the DC blocking filter, they've enabled the 2 FSK modulation, and right here they've enabled the Manchester encoding. So that's why we're seeing so much data coming back from the unit. If you know what Manchester encoding is, that's basically an XOR with the clock frequency. There's 2 basic ways that that's done. One's either looking at a 0 to 1 or a 1 to 0 transition and then encoding the data off of that. So what we need to do with our LabVIEW program is to take this Manchester encoded data, which is what we have, and back that out to get back to our original raw data. Just looking at our updated LabVIEW app, and again we are just opening up the file, and I display the number of bytes that we've read, and from there I'll read the entire contents of the file and I'll create this unsigned byte array. I then compare each byte for a 3-1 or 3-0 to decide if it's a 0 or a 1, and what I'll do is I'll generate a binary array, which then I can go ahead and process. What you see here, this is looking for my 4 consecutive bits to be the same, and this is what my trigger is. And I'll remove all the data that's prepending the trigger. And from there I'll create a new array, which is what I'm going to start working with. And again, because we're doing a 4x oversample, I'll go ahead and I'll decimate this array. And then what I'll do is I'll check all 4 bits to make sure that they match. And if they do, I'll go ahead and I'll store that into my binary decimated array. And the next thing I do is I'll run my Manchester decoder, and then I'll take that data and I'll put that back into a binary array, and then from the binary array I'll convert that into an unsigned byte array, and then I'll take that into our friend's little LabVIEW decoder app and we'll print that up on the display. So this is looking at the main panel, and we can go ahead and run this, and we'll just load up our binary data that we had just loaded off of our scope. And so you can see here in the upper left, this is our raw data. It starts out at 3-1, 3-1, 3-1, 3-0, 3-0, and then we convert that into the raw binary array. I then strip out these first 3 bits while I'm looking for the first nibble to match. And you can see again I've skewed the data, so then I go ahead and decimate the data, and you can see it's captured a total of 298 bits. So this is my Manchester encoded data here. I'll back that out, and this is now my raw data. So I've got AA, 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 AA. Remember looking at that last data that I showed you off the LaCroix scope, the registers were programmed up for sending 4 preamble bytes, and the preamble is defined as an AA. And then as we kind of look down here, here's our interesting data. 10, 20, 32, 47, 50, BB60C on down, and that works out to 0.99980 volts. This is another program that I wrote. So this is reading in our raw IQ file that we had created using Spike, and this graph is showing us the raw FSK data. So we can go ahead and zoom into this, and now we can actually see the various bits as they're being sent. Of course, we only need the one channel. I'm just working with the I channel. So what I'm doing currently is I run an FFT across each one of these bits, and I basically determine if it's a 1 or a 0 state that way, and then regenerate a bit array, which then gets converted back to this Manchester encoded byte array, and then again convert that back to the raw data. So for the next step, I want to pull the data directly into LabVIEW from the BB60C. So I'm using the API that they supply. The small longer burst is from the multimeter, and the higher amplitude shorter burst is from the PC. So what I've done is I've set up a trigger that works similar to Spike's video trigger, and I'm waiting for the transponders both to be off for some length of time, and then I wait for the multimeter to turn on its radio, and I start collecting this data. So this packet is actually made up of multiple frames being sent from the meter, and you can see we can zoom into this and see our actual raw data, and again we can scroll through that. So as I'm pulling the data out of the BB60, I go ahead and decimate it. I'm only interested in the I data. So as this frame gets built up, I can go ahead and send that data down to my decoder. All I've done with this program is I've taken this array and I've copied it into our decode software, and again I just run our FFT across this data, and I decode this back into a bit stream, and I recreate my Manchester encoded byte array and convert that back to the raw data, and then again decode our LCD. So my next step will be to combine these two programs. So here's the money shot. We can see our antenna off of the signal hound in the background. The battery is pretty much shot now on the meter. Here's our dongle. And again, the meter is attached to our signal generator. And this is the output voltage here. This is again our FSK data. We can zoom into this. Of course, this is our digital readout up here, and I'm plotting the AC waveform off of it. And of course, this is the standard Extech software. We can go ahead and change the frequency. Let's just slow that down. And it is running a little bit faster. So there you go. This is the BB60C from Signal Hound, totally decoding the Extech meter with a little help from LabVIEW. No problems at all. I think that's going to be it for the video. Hope you enjoyed it. Till the next meter. Later.